Hi, and welcome to the Chapter 7 lecture for Chem 100. Chapter 7 is all about attractive forces. These are forces that hold molecules together, and they're not quite as strong as bonds, but they do have strength, and they're very important in chemistry and in biology. So we're going to talk about the different types of attractive forces. We'll talk about how they contribute to the states of matter, and like liquid, solids, and gases. We'll also talk about how attractive forces contribute to solubility rules, what dissolves in what, and then maybe you'll understand this cat meme joke over here. We'll talk a little bit about it, applying attractive forces to dietary lipids and fats, but we'll talk more about those in a later unit. And then lastly, the importance of those attractive forces in biological organisms at the cellular level. So, what are attractive forces? All right, so we've talked about bonds. Bonds are what we call intramolecular forces. These are forces that are within a molecule and hold the atoms together. So chemical bonds, ionic and covalent bonds, would be intramolecular forces, forces within the molecule. So for example, in HCl, this is a covalent compound where you have a bond, a sharing of 2 electrons. All right, so that's a strong intramolecular force. But between these 2 HCl molecules, these 2 molecules are attracted to each other through something called an intermolecular force. So the atoms within the molecule are held together through intramolecular forces or bonds, and intermolecular forces are these attractive forces that we're talking about that attract 2 molecules together and have them interact a little bit. So they're much weaker than intramolecular forces. They're much weaker than bonds. I like to think of it as almost like a game of Red Rover. You ever played that game where a bunch of people stand in a line and they hold hands, Red Rover, send so-and-so right over, and then the person comes running over and tries to break through the chain link of hands. All right, so the hand holding is like the intermolecular force. It's 2 people connecting with each other. And that hand holding is pretty strong, right? Sometimes you catch the person, they can't break through. Sometimes they can break through, right? But what I don't think ever happens is that somebody busts through and the hands stay together, but like somebody's arm comes off, all right? That will never happen because your arm being attached to your body, that is a strong bond that your arm has to your body. If any thing is going to break, it's going to be that connection between the 2 hands. So that's sort of my analogy for intramolecular forces, bonds, versus intermolecular forces, these attractions. Okay, so these attractive forces ultimately, they come in different strengths, but they all basically have the same mechanism. So they basically all involve attraction of positive to negative charge, like an ionic bond, except in an ionic bond you have a full positive charge and a full negative charge. We're going to talk about how, and we've talked about with covalent bonds, how covalent bonds involve sharing of electrons, but that atoms don't always share electrons evenly or equally in a bond. So you may have 2 atoms bonded together, but one of them is very electronegative, so it hogs those electrons and it becomes partially negative, and then the other one who's getting electrons hogged from it becomes partially positive. We get these dipoles, these polar molecules. So attractive forces have to do with these partial charges attracting each other rather than full charges in an ionic compound. So the different types of attractive forces are listed here in order of weakest to strongest. Now technically at the very bottom here we could have a 5th layer, and that would be ionic bonding, because it is an electrostatic attraction between negative and positive, but it is it is a type of bond, so I don't like to include it here. I just like to include the attractive forces here. Okay, so London forces are the weakest type, and we'll talk about what they are. This is a good sort of cheat slide. You might want to like star this slide as a good way to remind yourself of all of these different types of attractive forces. So we'll go through them all in detail, and then how about I'll come back to this sort of summary slide. So we're going to start with London forces. All right, so London forces are also called London dispersion forces, or dispersion forces, or induced dipole. They go by a couple of different names. I tend to use London, or I'll sometimes call them LD for short, London dispersion. And so what they are an induced dipole. So London dispersion forces happen in all molecules. All molecules have them, but they are the only attractive force that exists in nonpolar molecules. So in a nonpolar situation, you have a bunch of atoms that are not polarized, all right? But remember, electrons, if this is an atom and this is the nucleus, electrons fly around in this cloud, right? So they're constantly moving. So sometimes, for a split second, you have a situation where there's more electrons flying around on the left than on the right. And then what you end up with is a slight, very tiny little dipole in this atom where it's partly negative and a little bit more positive near the nucleus. And then when that happens, that partial positive charge is going to attract electrons from the cloud of the neighboring atom, and that will induce a dipole in the neighboring atom. So even in totally nonpolar situations, you can have these little instantaneous temporary dipoles that form just because electrons are flying around. And when they fly around, then they can make these little dipoles that then induce a dipole in the next cell. So we call this atomic polarization, when the atoms become temporarily polarized. So temporary is a key word here when we're talking about London dispersion forces. You get temporary dipoles, all right, from these electrons flying around, sometimes leaning towards one way or the other. And so it's a very weak attractive force because those dipoles are temporary. So that attraction is only temporary for these little instantaneous, split seconds in time. But that's if it's a small molecule, if there's just a couple of atoms, right? But the more atoms that are in a molecule, the stronger these forces become because they're additive. So if you have 2 atoms, that's going to be a pretty weak attraction. But if you have 100 or 1,000 atoms in a molecule, then that force starts to become fairly significant. So the rule with London dispersion forces is the larger the molecule, the more London forces it has. So I do like to clarify that dispersion forces exist between all types of molecules, but it's such a weak force that in other types of molecules, when we start talking about stronger forces, London dispersion is really has very minimal effect. So it's really, London dispersion forces are really most important for nonpolar molecules. Remember, nonpolar molecules are going to be anything that contain just a bunch of C's and H's, carbons and hydrogens, if we're talking about organic chemistry. No electron hogs, no fluorine, oxygen, nitrogen, or chlorine. So a good example of London forces in action is it's how cling wrap works, like, what do you call it? Saran wrap. So saran wrap is a polymer, a nonpolar polymer, just made up of carbons and hydrogens. But when you unroll it, that causes the electrons to disperse unevenly, and you get that static, the static cling of the wrap. Okay, the static is caused by electrons moving, and then that polarizes the material, and so it's attracted to itself, and so you get this sticky adherence That's that attractive force that you can feel when you stick the saran wrap to something or if it sticks to itself. Okay, but it's not that strong of a force, right? It's not stuck. You can easily unwrap things. So it's strong enough to seal something off, but it's not so strong that you can't easily open it back up. So that's a great example of London forces in a nonpolar substance that you can sort of feel or see at work. The next strongest type of attractive force are dipole-dipole interactions, and these occur between two polar molecules. All right, polar molecules have permanent dipoles, right? They're not sharing equally, and so you have one end that's permanently partially negative and one that's permanently partially positive. So when you get these guys together, they attract. Their opposite ends attract, whether they're stacked or whether they're sort of horizontally. They're going to attract each other. So here's an example, acetone, which is an ingredient in, well, it used to be in a lot of nail polishes. It's a good solvent. It dissolves lots of things. So we've got this molecule, it's got CH3, CH3, those are nonpolar parts. But then there's this oxygen here. Sorry about that. So this oxygen is an electron hog. It's going to hog electrons. So we'll have a dipole moment moving up. In other words, the electrons from these parts will be hogged towards that oxygen, and you'll get a dipole where the oxygen is partially negative and the carbon is partially positive. And so these molecules will actually line up and be attracted to each other through those dipoles, and that will help keep them together. So the larger the dipole moment, in other words, the more polar the molecule is, the stronger that attraction will be, because the larger those partial charges will be. The third type of attractive force is hydrogen bonding. Now, hydrogen bonding is actually just a really strong dipole-dipole interaction, and so it gets its own category. The thing I hate about hydrogen bonding is this word here, bonding, because it's not a bond. It's not. Bonds are intramolecular forces. We have covalent bonds and ionic bonds. Hydrogen bonds are attractive forces. They should really be called hydrogen attractions. All right, so this is sort of a misnomer. Don't get confused. Hydrogen bonding is technically not a bond. It's still an attractive force, but it's called a hydrogen bond, so that's what we have to call it. I will sometimes abbreviate them as HB, like when I'm doing sample problems. All right, so hydrogen bonds form because when hydrogen, which has a pretty low electronegativity, is bonded to any one of the top three electron hogs, F, O, and N, fluorine, oxygen, and nitrogen, it gets a really strong polarity. So when you have hydrogen that's bonded to a fluorine, for example, right, that partial charge on the fluorine is not small. It's actually a pretty big partial negative. And the partial charge on this hydrogen is pretty large. It's a pretty big partial positive. So because of that, it's a particularly strong type of dipole-dipole interaction. So in order to hydrogen bond, you sort of need two partners, two to tango. And so the first thing you need is a hydrogen that's highly positive. We call that a hydrogen bond donor. So it's a hydrogen that's bonded to an N, O, or F, as you can see here. So HN, HO, or HF. You need to have a very positive, partially positive hydrogen. All right, and then you need to have something partially negative for it to be attracted to. So basically, any NO or F, any electron hog on any other molecule, would be a hydrogen bond acceptor. It could hydrogen bond with any of these highly polarized hydrogens. Okay, so we have hydrogen bond donors over here and hydrogen bond acceptors, examples over here. By default, if a molecule has a hydrogen bond donor, it also has a hydrogen bond acceptor because it's going to have an F, O, or N on it because it has a hydrogen bonded to that. So if a molecule has a hydrogen bond donor, it can hydrogen bond with itself. Some molecules only have hydrogen bond acceptors, so they can't hydrogen bond with themselves because they don't have positively charged hydrogens, but they can hydrogen bond with other things that do have those positively charged hydrogens. Another thing that I'm not sure I pointed out that I'm noticing right now is that I have these red dotted lines drawn to show intermolecular forces. So the dotted line is very typical to show attractive forces because bonds are distinguished by a solid line because they are strong. So intermolecular forces are often shown with a dotted line. And really the only ones that we really show with dotted lines are these hydrogen bonds. They're particularly important in biological systems because they're particularly important in water. So water is basically just a little hydrogen bonding machine. That's not the right word, but so it's just two hydrogens and an oxygen. So it has two hydrogens that are partially positively charged and this one oxygen that's partially negatively charged. All right, so it is basically just a bunch of hydrogen bond donors and acceptors. So you have two hydrogen bond donors for every water molecule, two of these positively charged hydrogens, and you actually have two spots on that oxygen that can be attracted to hydrogens. So for one water molecule, a single water molecule can actually have 4 hydrogen bonds with 4 other water molecules. Notice that the hydrogens are attracted to the oxygens of the other water molecule. The oxygen is attracted to the hydrogens on the other water molecules. Okay, so water has a lot of unique properties because of its small size and its multitude of hydrogen bonds that it can have. And we'll get to that coming up. But notice again that the hydrogen bonds are usually drawn as a red dotted line or even as a black dotted line, but always as a dotted line, never as a solid line. So we can see that hydrogen bonds can exist between two of the same type of molecule. So here's two identical molecules that one of them's flipped upside down, and we can see that they are hydrogen bonding with each other. So this OH, that H here, has a partial positive charge because it's bonded to this O, which is an electron hog, and it's attracted to this O here, this electron hog that's going to be partially negative on this molecule, and same arrangement down here. You can also have hydrogen bonding between two different types of molecules. So here we have ethanol, pictured here, and a water molecule. So water and ethanol can mix together because they can actually interact with each other through attractive forces through hydrogen bonding because they both have OHs. And then lastly, you can have hydrogen in very large molecules. You can have hydrogen bonding within the molecule. So large molecules can fold up on themselves and actually be attracted to other parts of the molecule, and those hydrogen bonds can help them keep a certain shape. So let's do a quick sample problem. We're going to draw out some hydrogen bonds. So it says, can the following molecules hydrogen bond to water? If so, how many hydrogen bonds can each make? And let's draw them. So first, I think the first thing we should do is draw out our water molecule. So here's a water molecule, H2O, so 2 H's, 1 O. All right, these hydrogens, because they're bonded to oxygen, which is a hog, the hydrogens are going to be partially positively charged, and the oxygen's going to be partially negatively charged. All right, now if we redraw out this guy a little bit, I'm going to keep this part condensed, CH3, because this part is nonpolar, the carbons and hydrogens. So CH3, CH, CH3. But I'm going to expand out that alcohol group a little bit. So OH, remember, is an alcohol. So I'm going to draw it out O and H. All right, remember that any hydrogen bonded to FO or N is going to be very partially positive. We can call it a hydrogen bond donor, and this oxygen here is going to be partially negative because it's the hog and it's going to hog electrons in that bond. All right, so this negative charged oxygen can be attracted to this positively charged hydrogen on the water molecule up here. All right, and I could draw another water molecule over here, O, H, H. All right, and this oxygen would be, of the water molecule, would be attracted to this hydrogen on our given molecule here, isopropanol, I think. So technically, this oxygen can have two hydrogen bonds to water. It would bond to two separate water molecules, but I'm just going to draw it as if it's attracted to both hydrogens on this water molecule. So the technically correct answer is that it could have three hydrogen bonds, that this guy can make three hydrogen bonds. But if you, as long as you just showed me that it makes those two, that the oxygen, both the oxygen and the hydrogen on this molecule could bond to water molecules, that would be full credit in my book. How about this one? So this one has CH3, which is nonpolar, CH2, nonpolar, all right, and Cl. Now Cl is an electron hog. Chlorine is an electron hog. Remember, the electron hogs are F, O, N, and Cl. Phone call is my mnemonic to remember the 4 electron hogs. All right, but chlorine is not quite strong enough to make for hydrogen bonding. So only those top 3 contribute to hydrogen bonding. So in this case, this one will not hydrogen bond with water. There are no hydrogen bonds that it will have with water. It can have dipole-dipole attractions with water. So we can draw that out. Because chlorine is still a hog, it's going to have a partially negative charge. It just won't be quite great enough to be strong enough to call it a hydrogen bond. So maybe I'll just draw that chlorine, and it will have a partially negative charge, and that will be attracted to which part of the water molecule? The oxygen or the hydrogen? Hopefully you said the hydrogen, because it will be partially positive. All right, but this is not a hydrogen bond. All right, this, what I've drawn here, is a dipole-dipole attraction, just a regular dipole-dipole attraction. I'm going to call it dip. All right, because it doesn't meet the definition of a hydrogen bond, because that electron hog there is not an F, O, or N specifically. Okay. And then the last one here, we've got CH3CN. Do we have an F, O, or N? Yes, we do. We have an N, a hog here. So we can draw this out, CH3, C, and then I just happen to know that there's a triple bond here to the N, all right? And since this guy is an electron hog, it's going to be hogging electrons from this carbon, so it will be partially negative. And this carbon over here will have a partial positive charge. All right, so if we draw ourselves a water molecule, the question is, where is the hydrogen bond going to be? Okay, so this oxygen is partially negatively charged. It's not really attracted to this carbon though. This carbon, I mean, that would be, there is a weak attraction there to this carbon, but the bigger attraction is going to be to the bigger charges. And the hydrogen here is going to have a very big positive charge, whereas this nitrogen will have a very large negative charge. So this is where the hydrogen bond will be, between that negatively charged nitrogen and the positively charged hydrogen. Okay, and that's the only hydrogen bond that this molecule can have. There's no hydrogen donors. So these hydrogens here in the CH3, they are bonded to the carbon. They're not bonded to the nitrogen. So they're not going to be involved in hydrogen bonding. And that's the biggest mistake people make, is they start bonding all hydrogens. All right, but the only hydrogens that can hydrogen bond are ones that are directly attached to an electron hog, F, O, or N. So this one would have one hydrogen bond, and we just drew it. All right, the fourth type of attractive force is called ion-dipole attraction, and this happens when you have a full-on ion and something polar. So the classic example here is salt dissolved in water. So, sorry. Excuse me. So table salt, sodium chloride, when you dissolve it in water, it breaks up into the ions, sodium ions and chloride ions. And those positively charged sodium ions are attracted to the partially negative oxygen of water molecules, and the fully negative chlorine atoms or ions are attracted to the partial positive hydrogens of water molecules. So it's an attraction between, literally, an ion and a polar molecule, ion-dipole attractions. And it'll contribute to some of the solubility rules that we are going to see in a few minutes. So when you have a question and you're given a molecule and you're asked what types of intermolecular forces does it have, this is a great flow chart to use. So the first thing that you want to ask is are there any ions present? Is there an ionic compound like sodium chloride, or are there ions like sodium ions present? All right, if so, then you can end up with ion-dipole forces if there's a polar molecule there. But a lot of times ions will not be present. So then you have to ask, well, are there polar molecules there? So if we don't have ions that have a full charge, do we have anything with a partial charge? No? Okay, then we're just talking about a nonpolar molecule. That's just London dispersion forces. If there are polar molecules present, then we might have dipole-dipole attraction, or we might have this super strong dipole-dipole, which is hydrogen bonding. So then we have to ask, are there any hydrogens that are bonded to FO or N? And if there are, then we have hydrogen bonding, but if there are not, then we just are dealing with dipole-dipole forces. So this is, I think, a neat flow chart to use when you're trying to ask yourself, is a molecule, just based on its formula, what kind of intermolecular forces will it have? So another question type would be pairing up two different molecules and saying, identify the strongest intermolecular force that could exist between each of the following pairs of molecules. So we can start by saying, what are the strongest forces that exist within each type of molecule? So this molecule here in A, CH3, CH2O, CH2, CH3. This O here is a hog. It's an electron hog. That tells me that there's going to be a dipole. All right, that it's going to be partially negatively charged. All right, but there's no hydrogens that are attached to that oxygen. These hydrogens are attached to the carbon. All right, so that oxygen does not have a hydrogen attached to it, so it can't hydrogen bond with itself. The strongest forces that this guy can have with itself are dipole-dipole attractions. I'm going to say dip-dip. Should just call it DD. All right? Because it's polar. It's a polar molecule. Now the second one here is all carbons and hydrogens. So this is a classic nonpolar molecule. Remember, carbon and hydrogen have very similar electronegativities, so they share electrons pretty evenly. All right, so we consider this molecule to be nonpolar. And the only type of attractive force that nonpolar molecules have are those London dispersion forces. All right, so whichever is the weaker of the two forces is the one they can actually have that can exist between the two of them. Because remember, all molecules have London dispersion forces. So technically this molecule has both London dispersion and dipole-dipole forces. But this molecule only has London dispersion. So London dispersion is the only one they have in common. So that's the strongest type of force that could exist between them, the one that they share, those London dispersion forces. Okay, let's do the second problem here. So again, we have a molecule with a polar molecule because it's got an electron hog. I'm going to write that little partial negative charge here. Say this one is polar. And I look at the second one, and there's also an oxygen here with a partial negative charge, another polar molecule. All right, so polar, neither of these oxygens, though, have any hydrogens attached to them. So there's going to be no hydrogen bonding, but each of these both have London dispersion forces, because everything has London dispersion forces, and they both also have dipole-dipole attractions because they're both polar molecules. So these two have the same type of attractive force, and the strongest force that can exist between them is those dipole-dipole attractions. So the answer to this one would be dipole-dipole is the strongest intermolecular force that could exist between them. And then lastly, part C, we have this molecule here has an oxygen, the one on the right has an oxygen, so we're at least dealing with dipole-dipole forces on each. All right, but this one has an H bonded to the oxygen. So that H is very partially positive and can be involved in hydrogen bonding. So this one, its strongest force that it has capability of is hydrogen bonding, and this one's strongest force is dipole-dipole. London dispersion is true of both of them, and dipole-dipole. But here's the thing. Remember, with hydrogen bonding, you only need one of the pairs. You only need one of the molecules to have a hydrogen bond donor. This hydrogen here, if I draw the dotted line, can actually be attracted to this oxygen here. So even though if you had a bunch of these molecules just by themselves, all right, the strongest force they could have with themselves are dipole-dipole because there's no hydrogen bond donor. But if you mix them with something that has a hydrogen bond donor, they can be involved. They can serve as a hydrogen bond acceptor. So in this case, hydrogen bonding is actually the strongest force that they can have together. All right, I'm going to say that this one here has hydrogen bonding in parentheses. It can hydrogen bond with other things because it has a hydrogen bond acceptor, but it can't hydrogen bond with itself. But since it's mixed with this molecule here that has a hydrogen bond donor, then in fact hydrogen bonding is the strongest force that exists between them. Ta-da! Okay. So these attractive forces, London forces, dipole-dipole attractions, hydrogen bonds, are so important in biology. They are the reason that certain molecules are the way they are and have the properties they have. So some really key examples are DNA and the cell membrane. So DNA, deoxyribonucleic acid, is your genetic material. It's the molecule of inheritance that's found in the nucleus of your cells. And it's designed in such a way where it is two strands that are joined together and wrapped around, and they store all the code for all the proteins in your body and instructions to build your cells. Now, those instructions are pretty important, and we want to keep them tucked away in the nucleus, and we want to keep them zipped up so that the molecule is stable. But if we want to make proteins in a cell, we have to unzip that DNA and basically read it and read those instructions, read that instructional code. And so you want the DNA to be zipped. I mean, I keep using this term zipped. That's a common analogy. A zipper, right? It holds your coat closed tightly to the wind, but then when you need to open it, it's very easy. You just swoop and it opens up very easily. So that's kind of how hydrogen bonds are. They're strong enough to keep your DNA together and keep it stable, but they're also weak enough that if you need to separate the strands of DNA, you can do so fairly easily. If those two strands of DNA were like covalently bonded together, it would take an immense amount of energy to unzip the DNA in order to replicate it and make new cells, or in order to read it and make proteins. So those hydrogen bonds are like the perfect strength. They're strong enough to keep it closed and stable, but easy enough to unzip when you need to. And London forces, although they're very weak, remember the larger the molecule, the stronger that London force adds up to be. And it turns out London forces are really important in holding our cells together. So your cell membrane is made up of a bunch of nonpolar fatty acids or lipids. And these nonpolar lipids are held together primarily through London forces. Now, with a cell membrane, cells should be flexible. They need to be flexible. And see, these purple things are proteins. Proteins will get inserted in cell membranes, and then sometimes they get removed. They can move around the cell membrane. And so in order for this membrane to be flexible, you need it to have relatively weak forces. So London forces hold this together, and they're weak enough to allow things to flow. So these proteins can actually like swim or move through the membrane if they need to. Like, think of just a bunch of balls floating on the surface of water, all right? But they're strong enough still to stay together because these molecules are large enough that those London forces are strong enough to keep that membrane together, but keep it fluid and keep it flexible. So it's, again, just right for the purpose of that structure. You want it to be fluid, but you also want it to be stable. So attractive forces also contribute to state changes. State changes are changes between solids, liquids, and gases, the different states of matter. When we heat up a substance, the molecules move around faster, right? Do I have that? No, okay. In a solid, you have the molecules are just kind of shaking a little bit, just vibrating, all right? But when you heat them up, they start to move faster, and then they can roll around each other, and that's what's happening in a liquid. And then you keep heating them, and now they start flying around everywhere, and now what you have is a gas, molecules that are really not interacting with each other at all, and they're flying around at high speeds. So these state changes, going from solid to liquid is melting. Going from liquid to gas, or going from liquid to solid is freezing. Going from liquid to gas is vaporization, and going from gas to liquid is condensation. There's another one that's fairly common, and going from solid to gas is sublimation, but we won't go there. But you should know these terms: melting, freezing, vaporizing, and condensing, what direction we're going. So the way that attractive forces contribute to this is attractive forces are what actually hold these atoms or molecules together in these different states. And by adding heat and making them move faster, adding energy, we start breaking those intermolecular forces, and that's what allows them to go from state to state. So state changes are actually due to interruption or breaking of these attractive forces, not chemical bonds. These are not chemical changes. These are physical changes. Basically, if you use my analogy from the earlier slide of that intermolecular forces are like a bunch of molecules holding hands, all right, they're no longer holding hands when they go into that gas phase. You're breaking those hand holding, but you're not actually breaking the molecules themselves. So when we go to a liquid, from a liquid to a gas, we call that temperature that changes the substance from liquid to a gas. That magic temperature is called the boiling point. And at the boiling point, you get boiling, you get air bubbles coming up from the bottom to the top. Those are the molecules turning into a gas. All right, and so in order for a substance to reach its boiling point, it needs to meet sort of two things. First, you need to have enough energy for those molecules to overcome their intermolecular forces, their attractive forces. So there's forces between each of these molecules that are holding them together. So you have to add enough heat to break those forces. You also need to have enough pressure coming off of the liquid to fight atmospheric pressure that's pushing down on it. So atmospheric pressure pushes down on this liquid, so that gas pressure needs to build up until it matches the atmospheric pressure, and then the gas bubbles can actually leave. All right, so we'll talk about, like, at different altitudes, you have different boiling points, because at different altitudes there's different atmospheric pressure. The higher you go in altitude, the lower the atmospheric pressure. So Denver is the mile-high city. It's got a very high altitude, and water boils there at a slightly lower temperature because the atmospheric pressure is lower, so you don't have to get it quite as hot in order for it to boil. This question here, which would have a higher boiling point? A molecule with strong attractive forces or a molecule with weak attractive forces? Which do you think would require more energy? Hopefully you said one with strong attractive forces. The stronger the forces, the more energy you have to put in to break them. So the higher the boiling point will be. Will need to be. Yes. So let's look at some specific molecules and their boiling points. So let's start with some alkanes, some simple straight chain hydrocarbon molecules. We've got pentane here, which has 5 carbons, and octane, which has 8 carbons. Pentane has a boiling point of 36 degrees Celsius, whereas octane has a boiling point of 125 degrees Celsius. These two compounds are very similar. They are both nonpolar because they're just hydrocarbons, which means that they have what type of intermolecular force? Hopefully you said London dispersion forces. That's the only force that nonpolar molecules can have, right? But they still have very different boiling points because remember, with London dispersion forces, the larger the molecule, the greater the London dispersion forces. So both of these have London dispersion forces. They have that in common because of their nonpolar structure, all right? But the London dispersion forces of the octane are greater than the London dispersion forces of the pentane because it is larger, all right? So the larger molecule, there's more atoms there to have temporary dipoles. And so there's more London dispersion forces, and that makes it have a higher boiling point. And we can see this trend with alkanes. If we look at the smaller alkanes, methane, ethane, propane, their boiling points are very, very low, which is why they are all gases at room temperature, because they boil at very cold temperatures. So at room temperature, they are gases. But as we get larger and larger, go down to octane. Octane, remember, is a major component of gasoline, which is a liquid, all right? It has a higher boiling point of 125 degrees Celsius, okay? So these are all going to be liquids at room temperature. And that's because, again, larger molecules have stronger London forces. Now let's look at these two alkanes, all right? These two alkanes are isomers of each other, so they both have the chemical formula, the molecular formula of C6H14. They have the same number of carbons and hydrogens, so they're the same size in terms of mass, all right? But yet they still have different boiling points. Hexane has boiling point of 69 degrees Celsius, and 2,3-dimethylbutane, this isomer of hexane, has a boiling point of 58 degrees Celsius. So why is that? All right, and it has to do with their shape. Okay, so shape also matters. I like to use this analogy of, all right, if we draw out the skeletal structure here of the hexane, all right, hexane looks like this. And so hexane molecules can stack really nicely, all right, because they're relatively straight. And because of that, you can get all these little dipole-dipole attractions, and not dipole-dipole, London forces, London dispersion forces, because there's just more contact. I like to say they spoon better. You know, like when you lay in bed with someone and you curve your bodies together like spoons. All right, spoons in a drawer fit really nicely together. They stack well. So that's what happens with straight chain alkanes that are straight. They can spoon better. And so their London dispersion forces, they can really have a lot of London dispersion forces. But this one here is kind of spiky. All right, think of like two people in bed and who, you know, sleep all sprawled out, okay? They can't spoon as well together because they just can't get as close to each other because of those groups that stick out, those arms that are sticking out. So there's fewer London dispersion attractions just because the molecules can't get as close, physically as close together. So the London dispersion forces in straight molecules, straight. Yes, Lena.
Is it done?
No, it's not done. I'm still recording. And versus, we'll say branched. Just slow it, writing with my cursor. All right, so the London forces in a straight chain alkane are greater than the London forces in a branched chain alkane. So shape, size, and shape. So the previous slide we could say size matters. This slide we would say shape matters for the boiling points of alkanes specifically. When we're talking about London dispersion forces, they're weak, but they are additive, so they do get stronger with size, and they're also stronger with shape. The straighter the shape, the higher the London dispersion forces are. So that's sort of the rule here. For alkanes with the same number of carbon atoms, straight chain alkanes will have higher boiling points than branched chain alkanes. So an example of this too in real life is in fats. Lipids they contain these long chains of hydrocarbons, all right? And some lipids are saturated. We have saturated fats that have straight chains of alkanes, and then we have unsaturated fats, which have double bonds, which cause the chains to be bent, and so they don't stack as nicely. They don't stack very well together, and so their London forces are weaker, which is why fatty foods that are high in saturated fats tend to be solid at room temperature, whereas those that are high in unsaturated fats are liquids at room temperature. They have weaker forces. Got a little young chemist in the background here making an appearance. So what about water? We just talked about these relatively large alkanes. Pentane has 5 carbons and 12 hydrogens, and its boiling point is 36 degrees Celsius. but water is just one oxygen and two hydrogens. It's a small, very small molecule, much smaller than pentane, but it has a higher boiling point. Okay, we just got through talking about how size matters. But so then how can this pentane, which is large, have a higher boiling point than water, which is small? So size matters, yes, when we're talking about London forces. But always, always, the stronger the attractive force is, that will trump. So water has hydrogen bonding. Hydrogen bonding is much stronger than London forces. So a molecule with a fair amount of London forces, like pentane, will still have a lower boiling point than something like water, because water has a much stronger attractive force, hydrogen bonding. It takes more energy to break those hydrogen bonds. So the sort of rules to follow here, if you're given two molecules and you're asked which one has a higher boiling point, all right, if you're given two nonpolar molecules, then it's going to be whichever one is larger and straighter. Whichever one is larger and straighter has more London forces and will have the higher boiling point. You want your iPad?
Yeah.
Take it.
I done my work.
Okay. If you have two molecules with different forces, all right, so one has London forces and one has dipole-dipole, or one has just dipole-dipole and the other has hydrogen bonding, right? Whichever one has the stronger force is going to have the higher boiling point. And then lastly, maybe you have two molecules with the same strong force. So maybe you have two molecules that can hydrogen bond. So how do you know which one has the higher boiling point? It'll be the one that has more hydrogen bonds, the one that has more partially positively charged hydrogens, for example. So let's do a couple of practice problems here. We've got pairs of compounds. We want to know which substance will have the higher boiling point. So the first thing I'm going to do is ask what type of attractive forces they have. All right, so remember attractive forces here. Well, maybe I'll make some steps out here. Okay, one. What are their attractive forces? I'm just say what forces do they have? And remember that flow chart. Basically, we want to know, if we want to know what forces they have, we need to know, is it ionic? Is it covalent? If it's covalent, is it polar? So are either of these ionic? No, there's not a non-metal and a metal. There's no metals here. So these are both covalent compounds. So I'm going to say ionic or covalent. And if covalent, is it polar or nonpolar? Polar, or I'm going to say NP for nonpolar. And these will help us, these are questions that are going to help us identify what the forces are. All right, so here we have two covalent compounds. This one has an oxygen. It has an electron hog. And remember, anything that has an electron hog, for all intents and purposes in this class, is a polar molecule. So this one is polar. So we've got that going for us. And this one is nonpolar. So that right away is going to tell us that this molecule here, the only types of attractive forces it has, the strongest and only type of attractive force it has, is London dispersion forces. All right, this polar molecule over here also has London dispersion forces. Everything has London dispersion forces. All right, but its London dispersion forces are going to be overshadowed by the fact that it's polar, so it also has dipole-dipole bonding. All right, and that oxygen is bonded to a hydrogen, so it also has hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular force it has, and will be the dominant one and overshadow these other ones that are weaker. All right, so since these two molecules are similar in size, but they have different forces, the one with the stronger force will have the higher boiling point. In this case, it's our polar molecule with hydrogen bonding. This one's going to have the higher boiling point, okay, because it has the strongest force. Now let's go over to B. In this case, we have two hydrocarbons. All right, both of these are just carbons and hydrogens. They're both nonpolar, so I'll put an NP. All right, so they're both nonpolar, and that means they both have London dispersion forces, right? That's the only thing that nonpolar molecules can have. So then we have to ask which one has more London dispersion forces. Well, these molecules are the same size. They both have 4 carbons and 10 hydrogens, if we counted them out. All right, but they do have different shapes. And remember, the straighter the shape, the greater the London forces. So this one's going to have greater London forces, which means it will have the higher boiling point. All right, and then lastly, part C, where again, we need to know what forces it has, so we need to ask, are they polar or nonpolar? Well, this one has a nitrogen, which is going to make it polar. And this one has an oxygen, which is going to make it polar. So that means they both have London dispersion forces. Everything has London dispersion forces. They both have dipole-dipole forces because they're both polar. So D, D. All right. And now we need to ask, do any of them have hydrogen bonding? So this nitrogen is bonded to a hydrogen, so it also has hydrogen bonding. And this water molecule here, or sorry, this methanol molecule here has an oxygen that's bonded to a hydrogen. Man, so this one's tricky. They both have hydrogen bonding. So then which one has the higher boiling point? All right, so this one has, if we drew it out, CH3, N, H, CH3. All right, this nitrogen has 1 lone pair. So that means that we can have 1 hydrogen bond here, and we can have 1 hydrogen bond here. The hydrogen can hydrogen bond with something, and that nitrogen can be an acceptor. This one, CH3, O, H. All right, so this OH can engage in hydrogen bonding. The oxygen technically has 2 lone pairs, so it can have 2 hydrogen bonds. Oh, everyone's interrupting my lecture video today. And this hydrogen, which is partially positively charged, will also have 1. So technically this molecule can have 3 hydrogen bonds, and this one can only have 2 hydrogen bonds. All right. Another way that we can distinguish these two also, since it's just the nitrogen has a hydrogen and the oxygen has 1 hydrogen, all right, is that oxygen is a bigger electron hog than nitrogen. Phone call, just to remind you of our electron hogs here. Phone call, F-O-N, and then I'm going to put Cl in parentheses because it's not involved in hydrogen bonding, but it's still a hog. All right, O is a bigger hog than N. All right, it has greater electronegativity. So that's another way you could tell that these hydrogen bonds are going to be stronger because it has a higher electronegativity. So either way you look at it, the electronegativity of that hog, nitrogen versus oxygen, or the number of hydrogen bonds, this one on the right here will actually have the greater boiling point, because although they both have hydrogen bonds, this one has stronger hydrogen bonds because oxygen is a stronger hog, and also oxygen has technically two acceptor points for more to bind to two different hydrogen bond to two different things. So we've talked about how attractive forces contribute to state, physical state of things, and that contributes to their boiling point and their melting points. But it also contributes to solubility, whether two things dissolve in one another. So the golden rule of solubility is like dissolves like. And what we're talking about here is things that have similar polarity. So nonpolar dissolves nonpolar, and polar dissolves polar. So this is why things like when you make salad dressing with like vinegar and olive oil or water and olive oil, all right, the oil and water parts don't mix. They stay separated. You have to shake it up and you can mix them temporarily. But that's because oil is nonpolar and water is polar, and those things don't like to mix. Similarly, when you get like an oil spill in the ocean, the oil floats on top and you have to use these skimmers to remove it because the oil and water don't mix. Polar and nonpolar things don't mix. So now hopefully you get the polar bear joke. All right, so here's an example of nonpolar dissolves nonpolar. So if you have two nonpolar things, they will mix together. All right, but why oil and water don't mix is because oil is nonpolar. It's a hydrocarbon. It's basically mostly hydrocarbons, and water is very polar. So they will remain separated, which is why this joke is funny. It's a water molecule saying, I'm sorry, we just can't be together. And this is a fat, a lipid molecule, crying and saying, is it because I'm fat? And yeah, kind of is, because fat is nonpolar, and that is why you guys can't be together. So the other like versus like dissolves like would be polar things can dissolve polar things. So that's because they can engage in either dipole-dipole interactions or hydrogen bonding together. So a classic example is sugar in water, or tea here. Sugar is made of a molecule called sucrose, and this is what sucrose looks like here. It's these two rings of carbons and hydrogens and oxygens, lots of oxygens, all right, and lots of OHs, so lots of hydrogen bond potential. So it can hydrogen bond with water because water is polar, the sugar is polar, and they both have hydrogen bonding sites. So you get some really good, strong interactions there, and that's why sugar can be dissolved in water. Sort of maybe an exception or an addition to that rule of like dissolves like. Polar dissolves polar, but polar can also dissolve ionic things. And that's because of those ion-dipole bonds. So we talked about salt, sodium chloride, can be dissolved in water because the sodium and chloride ions separate, and then they can engage in ion-dipole bonds with water. So I'm just going to comment that these are ion dipole bonds that we're seeing down here. All right, these dotted lines represent ion dipole bonds between the sodium and the chlorine with water molecules. Notice that these little circles are slightly different. The sodium, being positively charged, is attracted to the oxygens on the water molecules because they are partially negatively charged. Whereas in around the chlorine ion, the water molecules are flipped because it's the partially positively charged hydrogens that are going to be attracted to the negatively charged ion. So this process of dissolving something in water is also called hydration. The hydration of a salt, in this case, the salt sodium chloride, but any salt, this could be any salt. And a salt, just a reminder here, or maybe a preview, is any ionic compound. Ionic So we classically use table salt, NaCl, as a salt when we're talking about it in chemistry, but in chemistry, any ionic compound is actually a salt. So this doesn't have to be sodium chloride. It could be magnesium chloride or magnesium bromide or lithium oxide. I don't know, lots of different salts could do this. So let's do another sample problem here. For each of the following pairs of compounds, predict whether they are likely to be soluble or not soluble in each other. And otherwise, we're looking for it. We've got to remember that golden rule of like dissolves like. Like dissolves. Maybe cursive will be better. Like dissolves like. All right. So again, when we're doing this, we need to determine, are these things polar or nonpolar? Or ionic is the other option. All right, so in this first problem, we've got water. Water is polar. And we have cyclohexane. And cyclohexane is an alkane. It's just carbons and hydrogens. So it is nonpolar. All right, can you mix something that's polar and nonpolar? No, you cannot. These are not soluble. All right, so I'll just do like an X. All right, these are not soluble. The next one, CH3OH, that hog right there tells me that this is polar. That electron hog oxygen tells me this is going to be polar. And KBr, K is a metal and bromine is a nonmetal, so this is actually an ionic compound. All right, can polar and ionic substances mix? They're not like, but they can mix because of ion-dipole attractions. So that's that exception to the like dissolves like, and they can dissolve or be soluble in each other because of ion-dipole forces. And then lastly, we've got two molecules here. This one has an oxygen, which tells me it's polar, and this one has an oxygen also, which tells me it is polar. Two polar things are alike. They are soluble because like dissolves like, and they are both polar. In this case, this molecule has an oxygen. It's not bonded to any hydrogens, so it has dipole-dipole as its strongest attractive force. And this one has an OH. That OH can do hydrogen bonding. And remember, you just need one donor to do hydrogen bonding. So this hydrogen here could hydrogen bond to this oxygen over here. So hydrogen bonding is the attractive force that's involved in these two things being soluble with one another. They can hydrogen bond. So we said that like dissolves like, polar and nonpolar don't mix. But there is this sort of magical sort of substance that can make polar and nonpolar things mix. And so that's what we're going to talk about here, the magic of soap. So soaps actually help you dissolve nonpolar substances in water, a polar substance. So soaps are fatty acid salts. And otherwise, they have this long hydrocarbon tail, which is nonpolar, but then they have an ionic group on the end. And ionic groups are very strong. They're like more than polar, right? They're the ion-dipole bonds are the strongest. So you have this very charged end, and then you have this very nonpolar end. So we call these types of molecules amphipathic. They are both polar and nonpolar at the same time. They have a polar head and a nonpolar tail. So they kind of bridge the gap between polar and nonpolar things. We say that the polar part, the charged part, is hydrophilic, it loves water, and that nonpolar tail is hydrophobic, it's afraid of water. And we say it's amphipathic. Amphi means both. Like amphibians live in both water and land. So amphipathic molecules are both nonpolar and polar. And so what happens is when you put these molecules in water, they form a very specific structure. They'll form these spheres. They'll clump together and form these spheres where the polar hydrophilic head groups are on the outside and the nonpolar hydrophobic groups are on the inside. And what can happen is dirt, all right, grease, which is nonpolar, it will have London forces and be attracted to the nonpolar tails, and they'll get trapped inside these little spheres. And so you basically get these little spheres that trap grease and carry it away in the water. Anything that does this, that is amphipathic like this, and that can help nonpolar substances dissolve in polar substances, we call them emulsifiers. And this sphere is called a micelle. So emulsifiers are any type of really amphipathic molecule that can form these micelles in water. And I really like this cartoon kind of showing how soap works. So you've got some nonpolar grease here, and the water molecules are trying to wash it away. They're like, come on, grime, let's get going. And the grime's like, no. And then the water's like, soap, I need you. And so the soap comes along, and all those nonpolar tails stick to the grease, and all of the polar heads follow the water molecules and carry it away. And that's really, like, it's cartoony, but it's literally what's happening when you are using soap to get rid of grease. All right, now, so soap is not the only amphipathic molecule that we use. In biology, there's several that are really important. So there are two types of fats that actually have charged head groups, and that we use them as amphipathic molecules and kind of as emulsifiers in biology. So phospholipids, which have a charged phosphate group and two hydrophobic tails, all right, and cholesterol, which has a charged or a polar head group and then a big nonpolar tail, right? These are actually really important in making up our cell membranes, and are important for so phospholipids are really important for transporting fats through the blood. They can form those micelles and help us, like when we eat fatty foods and we need to absorb the fats and transport them through the blood, which is mostly water and polar. All right, fats can't just travel willy-nilly through the blood because they don't mix. So we package them in these basically giant micelles that are made up of phospholipids and cholesterols, and it helps us to emulsify fats in our diet and also transport them through the blood. So these are some of the different structures that phospholipids can make. They can make micelles. They tend to make larger structures called liposomes, but either way, both of these structures can transport fats. And then the most important structure that they make is that phospholipid bilayer. And our cell membranes are basically entirely surrounded by that. So our cells are basically giant liposomes. They're just giant spheres that are made up of a phospholipid bilayer surface structure. So when we look at that phospholipid bilayer, what we see is that the hydrophilic heads line the inside and outside layers because there's water outside and inside of cells, and that's the part that likes water. And those tail groups, the hydrophobic tails, are all sort of in the in-between space interacting with each other. So these guys would interact through London dispersion forces. We've got London dispersion forces holding these guys together. And we have hydrogen bonding a lot of times going on inside and outside the cell with water. And so when you put these molecules in water, they will spontaneously take this shape because that's how they're most comfortable, with the hydrophobic tails being away from the water and the hydrophilic head groups being engaged with the water. So again, just another shot of the cell membrane, Remember, the cell membrane is made of lots of phospholipids, and then this yellow pieces are bits of cholesterol that are embedded in there. Remember, we said that it's held together through these London forces, so it's very fluid, and these proteins can essentially like swim through the membranes and move around if they need to. All right, and that model of the membrane, it's called the fluid mosaic model of the membrane. It's fluid in that these proteins and stuff can kind of swim through here, but they also, it's sturdy enough to actually hold that all of these phospholipids stay together and don't leak. So what does all this mean? What is the importance of attractive forces? They're kind of confusing, but they're actually super important. So basically, anything in this world that is solid is held together by strong attractive forces. If you didn't have attractive forces, you would fall through your chair. I mean, everything would be a gas for the most part. If there were no attractive forces, no molecules would be held together, would be stuck together, and everything would be in a gaseous state. So you yourself are also held together by attractive forces. Your membranes are held together by those London forces. Your DNA is held together by hydrogen bonding and all sorts of attractions in between. So I like to imagine that if we didn't have attractive forces in our bodies, this is what would happen to our bodies. This is a little movie clip from X-Men, the original X-Men movie. So this guy, he just totally loses, like his body sort of melts into liquid and then spills away and presumably also evaporates into a gas. So if we didn't have attractive forces, our bodies similarly would melt from a solid to a liquid, ultimately to a gas. We would just evaporate. So yeah, attractive forces are pretty important for holding our world together and holding it together in different strengths so that we have these different substances in different forms, gases, liquids, and solids. That is the end of chapter 7. Thanks for watching. Bye now.